My name is Fredrik Kjolstad, and I'm a new assistant professor in the computer science department at Stanford. I started March 1st, so I'm fairly new at this. My training is from MIT, and I'm a compiler researcher, so I'm very interested in compilers. And today I'm going to talk to you about a new, very interesting area for compilers and programming models, and that's the area of sparse applications. So you can think of it as compilers and domain-specific compilers and programming models for sparse applications. And we see a few interesting sparse applications on this slide. There's one from biology, there's a social network, and a robot. And there's some sparse neural networks there as well. So let me define a little bit what I mean by sparsity and also what I mean about irregularity. So I'm going to mainly talk about sparse and irregular systems. So I think of it in terms of the underlying system, so not in terms of a tensor necessarily. And a system is just a collection of objects. It can be anything from people to web pages to degrees of freedom in a finite element system. And these objects have connections between them. And if every object interacts with every object, meaning they have connections, then you have a dense system, and that's what you see on the left-hand side here. A dense system could be modeled as a dense matrix or as a dense full graph, and so forth. A sparse system is a system where not everything interacts with each other. For instance, everyone is not friends with everyone in the world. Most triangles don't distribute energy to most other triangles, and so forth. And in the middle here you see a sparse system that's regular. And regular means that in this case there's a fixed number of connections between each of them, and it's connected in a grid. So I do not need to store all the connections to know about the system. I can encode it with just two numbers, which is the width and height of this grid. And then we come to what I think is the most interesting and sort of least addressed area, and that's sparse irregular systems. And we often think of them as graphs, although I would say all of these systems are graphs. But we think of them as sort of graphs where things are just irregularly connected together. Some people have many friends, some people have fewer and maybe closer friends, and not all cities are connected by the same amount of roads, and so forth. And in these systems, we actually have to store the edges because there's no way to encode with very few numbers how these things are connected together because they are irregular. And these are the ones I'm going to talk about today. I'm going to talk about compilers for them. So here's some examples of applications that deal with these irregular and sparse systems. On the left, you see some computations from simulation optimization. There's a robot there, so some robotic system, finite element simulations in 3D movies, for instance, or any other optimization like that, molecular dynamics and so forth. And these are sparse and irregular applications, but then you also have machine learning where you're starting to see sparse convolutional neural networks and sparse neural networks and so forth. So sparsity seems to be interesting there too, not just because the weights might be sparse, but because what you're learning on might be sparse. Maybe you're trying to learn something over a social network or some other network. And then you have the area of data analytics, where you want to learn something, again, maybe from a social network. Maybe you want to learn a recommender system where you want to know which products someone are interested in based on the other products. This would be a sparse system because most people don't interact with most products and they don't review most products and so forth. So I'm going to propose that the way we think of domain-specific languages is not in terms of different areas of computation, like not in terms of physics or chemistry or machine learning. We should think of them in terms of mathematical abstractions. And these mathematical abstractions have been developed over centuries, and they're around because they apply to many areas. So the benefit of this is that once we build languages and language abstractions and language constructs for these abstractions, they will benefit many areas, which means that we can amortize the cost of actually building these things. And here's three very powerful and very useful mathematical abstractions. One is relations, so the relational algebra and databases and all of that. And they are really good for combining data to form one of the systems I've described. So you can use filters, you can use joins and so forth. Then there's graphs, which are really good for local operations, like Dijkstra's algorithm, or computing the energy of a triangle, or something like that. And then there's tensors, which are a big area recently with with neural networks coming along. And they are really good for forgetting about the pieces of the system. So I'm assuming the tensors are sparse in this case. But you hide all the details of the systems inside one tensor. And then you can treat it as one large single object in a high-dimensional space and forget about the pieces and just compute on the whole system at once. And I'm going to argue that none of these are the abstraction we should use. They're different tools for different jobs. And we want a compiler that can compile all of these. And now my next argument is, why can we not just write libraries by hand like we've been doing forever? Why do we need a language? Maybe we could just write up all the computations we need to do in C, or even lower level than C, and then just call them as functions. And this would save us a lot of work if there's a few of these functions, because writing a compiler is a lot of work. And my argument then is there's too many implementations you would need, so you can't write them by hand. And I'm going to argue this for the tensor algebra. So here you see some expressions in the tensor algebra. There's the linear algebra subset, which is just a piece of the tensor algebra. There's some expressions from data analytics here. These specific expressions, they're in the tensor algebra index notation, come from tensor factorization, where you're trying to factorize a tensor similar to a singular value decomposition to learn something about clustering, perhaps. And here are some from quantum chromodynamics. And in addition to all of those are just a few expressions. There's an countably infinite number of expressions in these algebras. And here are a few data structures you might want to compute on, because your data is irregular, so you have to store them in some data structure. And that's not a dense array. If you do, then you're going to have a lot of memory you need. So here's are a few common data structures for storing just matrices. And for each of these, you would need to compute all those expressions on the different data structures. Maybe you want your vector to be sparse as well, and maybe your tensor is sparse and stored in different data structures. And then maybe you have some more very speculative data structures, like my data is in a database, I just want to compute on it. And in addition to all of those expressions and all of those data structures, you might also want to compute your different functions on different machines, CPUs, GPUs. We're starting to see a lot of domain-specific architectures. Cloud computers are not going away. And the Cartesian combination of all of these expressions, infinite expressions, on an unbounded number of data structures, on an unbounded number of machines, is too many functions to write by hand. So you can write and optimize any of these by hand, that's fine. You can never write and optimize all of them, there's too many. So that's why we want a compiler, because then we can write a composable machinery that will generate these functions for us on demand. So let me give you two examples of why it's even more important than that. And these examples are going to show that if you don't generate expressions that simultaneously compute many operations in a fused manner, you're going to get asymptotically worse performance. With dense computation, that doesn't happen. What happens in dense computations is just you get poor cache locality, but in sparse computations, your asymptote depends on it in some cases. The first expression I'm showing you here is called sample dense-dense matrix multiplication, and it comes from one of the more important algorithms for tensor factorization. So in this computational kernel, you need to multiply a tall and skinny matrix C by a wide and short matrix D, and sometimes C and D are the same. So you do a matrix multiplication, and then you element-wise multiply the result of that by a sparse matrix B. So this could be something like you're computing some distance metric between all people on Facebook, and then you just want to sample out all pairs of friends, because those are the ones you care about distances between. So if you compute this as two separate operations, first a matrix multiplication and then the element-wise matrix multiplication, you're doing asymptotically too much work, because you would be doing a dot product to do the whole dense matrix multiplication, whereas the sparse matrix you're element-wise multiplying with requires you to only do a few of those dot products. And if there's very few non-zeros in the sparse matrix B, which is realistic, then you have done way too much work. And we see that in these results I'm showing. These are some matrices from Florida sparse matrix repository. And if you do these operations separately, you get very, very poor performance. Poorer and poorer performance, the more and more the system scales. But if you fuse them together, you get good performance. And here's another example from the relational algebra. Remember, I'm talking not just about tensors, I'm talking about relations, tensors, and graphs. What you're doing with this query, and this comes from Go and Rudra and Ray's work, you're trying to find, in this query, you're trying to find triangles in a graph represented as relations. And this is a common data analytics question you want to ask. So the minimum bound, worst case bound for this triangle query is of n to the power of 2/3. But what they show, what Go and Ray and Rudder show in the 2013 paper is that if you do these two joins, so these are two inner joins, if you do them separately in separately written computations, your worst case asymptote is n to the n squared, which is worse asymptotically than doing them fused together. So this is just another example. It's because the temper you might produce, the temper relation might be O of n squared large. They show that if you fuse together the operations, you can get to the true lower bound of the computation. So this is just another example. In sparse computations, you can't just separately write up all the two-way expressions or binary expressions. You have to fuse operations together. So what I'm arguing is that we should write a compiler to do this for us. And such a compiler, call it the sparse compiler here, would need to combine an algorithmic language that describes the computations, a scheduling language that describes how to do the computation, what order, where to store data, and then also a data representation language that describes the data structures you're computing on. And from that, I believe we can compile to CPUs, GPUs, and domain-specific architectures. So we will have a retargetable compiler because it will be working at a higher level. And we've written such a compiler for the Sparse Tensor Algebra. And this compiler is called the Sparse Tensor Algebra compiler, which we abbreviate to TACO. It takes in any computation or any expression in the tensor algebra. And then it takes in for each tensor what data structures are that tensor stored in. And then a scheduling language saying how to compute that expression on those data structures or that tensor. And then it produces code for CPUs and GPUs, and we're working on targeting domain-specific architectures. And this is available on GitHub under a MIT license. So the underlying ideas here is something we call sparse iteration theory. And that theory allows you to describe iteration spaces like in a polyhedron model with holes, irregular holes. And here's a matrix multiplication written in tensor index notation. And the sparse iteration space expression just replaces the multiplication by an intersection. And that's because if you multiply something by 0, you get 0. So you only need to do work in the intersection. And here's the model of the sparse iteration space. It's a polyhedral rectangle, but there's many holes in it. And we can break down the different the iteration space into per dimension iteration spaces, and those will result in the actual iterations we need to do. And sometimes this requires iterating over two data structures at the same time. So you might have to iterate over the intersection or the union of two or more data structures. We have these iteration spaces, but iteration spaces are not what we iterate over. We iterate over data structures. So here we're back to the same expression. And B would be stored in some data structure, and it would be stored in a hierarchical data structure. It stores basically a tree of coordinates. And the same with C. So you have two hierarchical data structures. And then you need to iterate over the intersection of the last dimension of B with the first dimension of C. So that's the iteration space of this computation if you're iterating over it. And we have this idea called a sparse iteration graph, where you can basically just order the different index variables. So those will be your loops. And then you can order them as a graph where you have I, J, and K as nodes. And then for each data structure you need to iterate through, which is B and C, you can draw paths through these graphs. So here you see B, you're iterating over IK, those two loops, by iterating through the data structure of B, which is two levels because it's a matrix. And the same with C. And then you have to do an intersection. And we know how to generate code to iterate over any such graph. So that's a very powerful thing to be able to do. Now you can iterate over sparse iteration spaces. Underlying this is the idea of a coordinate tree abstraction, where any tensor is represented as a tree of a coordinate hierarchy, or a tree of coordinates. In this case, you have a dense matrix on the left-hand side. Then you have the full tree representing that dense matrix in the middle. And if it wasn't a dense matrix, it was sparse, you wouldn't have a full tree anymore. Certain coordinates would be missing. And you can now take this tree or this hierarchy and you can order it level by level. And the key here is that you can assign a data structure to each level independently. So here we design the dense array to the top level. And then we can assign a compressed data structure, which is just a compressed list of coordinates to the second level. And now we recreated the famous CSR format for matrices. And you can compose data structures in any way. And they just compose hierarchically to represent any tensor. So that's a very powerful feature. And now when you generate code, what you need to do is generate code for each node in the iteration graph that co-iterate over all the data structures that are incoming on that node. We can also do optimizations like tiling and fusion and collapsing on these iteration graphs, but I don't have time to go into that. So you have tensors, and tensors lead to sparse iteration spaces, as I showed. And it's because the non-zeros are a subset of the Cartesian combination of those sets that form the dimensions of the tensor. For relations and relational algebra, you can also think of it as a sparse iteration space, and that is because a relation, by definition, is the Cartesian combination of the sets that each of the columns are drawn from, or each of the parts of the relation are drawn from. So if you take all of those sets and unfold them along the different dimensions of the iteration space, you have a sparse iteration space, extremely sparse. And then graphs can also be thought of as a sparse iteration space, because the graph edges are a subset of the Cartesian combination of all the nodes. So that gives you the iteration space. So there's an underlying commonality between these three mathematical abstractions. And what this means is that we can compile all three of them, perhaps, and I believe this can be done, with the same compiler infrastructure. And the most powerful thing about that is that you can now fuse together operations in the different abstractions. So you can maybe do a relational query to create some data, then compute on it as a tensor, or start as a graph, maybe a mesh or maybe an optimization problem, turn it into matrices and vectors, do an optimization, and then come back. And a compiler can now fuse across the boundaries, and then you can take this whole fused code and compile it to different machines. So here's one example. You have some relations, you do some filters, you join them together, and then you do some tensor operations. Maybe you're computing a regression, or maybe you're doing inference through a neural network. Here's another example that we worked on, and this is simulations of a mesh. It can also be used for optimization. You start with a hypergraph describing a robot or describing a mesh. You assemble a tensor from it, you compute or a matrix from it, you compute with the linear algebra, and then you store vectors back to sets on the graph. And what this lets you do is to do fused simulations or optimizations from the mesh through the linear algebra back to the mesh, and you can push the computations back onto the mesh so that you're computing in place without creating new data structures. So what I believe we need to do, we have these three mathematical languages. We have already a compiler for the sparse tensor algebra, but we need to create a new compiler that can compile the union of these three abstractions. And this lets us fuse things together. It lets us also target different machines like CPUs, GPUs, and cloud computers, and potentially domain-specific architectures too. It lets us change the data structures that store the relations and tensors independently of the programs we've written to compute on them. And this would be a very powerful system, and I'm very interested in working on this system. And I'm interested in talking to anyone else who are interested in opportunities for these sparse compilers and sparse computations. And I think they're going to be more and more important. And here are a few slides taken from the 2018 Turing Award lecture by Hennessy and Patterson called A Golden Age for Computer Architecture. And in this talk, they argued for domain-specific architectures because we cannot lean on Moore's law and Denner scaling anymore. And a big open problem they proposed is dealing with sparse data. And there's been some work in the architecture community to do that. We and others have done some work in the compiler community to target these domain-specific architectures, so you don't have to manually write your code by hand. I'm interested in continuing that work, and I'm interested in any thoughts, questions, and ideas our industry affiliates may have. So thanks a lot, and I look forward to some questions and some discussion.